So I hope you recall that a tautology is when the statement is always true. All right, take a look at this truth table here. We've got your atomics on the left, P, Q, and we've got phi. And phi is a tautology insofar as on all TVAs, it's true. It has to be all of them. So it's always true. A contradiction is when the statement is always false. By always, what we mean is all logically possible worlds, it is false. So again, you would expect the TVA, you would expect it to be false under all TVAs. Okay. Now, a contingent statement, or sometimes what might be called contingency, is when the statement is sometimes true and sometimes false, right? Most things we say in the real world are contingent, right? It's sometimes true, sometimes false. It depends on the way that the world is. Okay. So here is a table recapping what I've said. Now, notice that the tautology, the contradiction, and the validity of an argument requires you to show all of the TVAs, right? Okay. Now, if a shortened truth table can show us only one or possibly two TVAs, then can a shortened truth table show us that a sentence is tautological, a contradiction, or whether an argument is valid? No, it can't. It doesn't have what it takes. However, now notice this. A shortened truth table can show us that it is not a tautology, not a contradiction. Why? Well, a tautology is when the statement is true under all TVAs. Well, as soon as we show that it is false under at least one TVA, then we know it's not a tautology. Exactly. So the distorted truth tables give us a counter example to the tautology or contradiction. And you know what? It gives us a counter example to validity. So to say something's not valid is to say it's invalid. So a shortened truth table can show us invalidity as well. And that's super useful, right? Now we don't have to do the full truth table. We can just come up with one TVA to show us that an argument is invalid. Cool. Any questions? Okay, moving on. So just to sum up, it shows it can do a few things for us. It's getting a bit repetitive at this point, but it shows us the invalidity of an argument. It shows us a sentence is not tautological. It shows a sentence is not a contradiction. And it could actually show us a sentence is contingent, right? But this time we need two TVAs. Now, there's actually a few more things that a shortened truth table can show us. But we won't cover those things in this course. Can anybody think of what else it might show us? Now, remember, shortened truth tables can generate one or two TVAs for us. What else can it show? Okay, I'll give you a clue. So the other things that it can show pertain to two sentences. So we have two sentences side by side. What can we say about them? Okay, no answers. That's okay. I might just move on then. Okay, so here is a statement. And we're going to have to come up with a shortened truth table. So I'm going to give you a demonstration now of a shortened truth table. What exactly are we to do? Well, we have to show that this is not a contradiction. So we have to show that there's at least one TVA under which this statement is true. Remember, contradiction is always false. So we need to find a TVA where the statement is true. How do we do that? Well, take a look at the statement. We have to find the main logical operator here. What might that be? Can somebody tell me? This test you're passing. Good. It is the conjunction. Okay. Now we know that the conjunction is the main logical operator. And what we want to do is find a TVA under which this statement is true. So what we can do is write a T above the conjunction. And we're going to sort of work backwards. And the key here is to find the truth value assignments of the atomics. So we might write the atomics on the side like this, draw a little table. And what we want to do is find the truth value assignments for these atomics. We might say it's true or false. That's showing that the statement is not a contradiction. To find the truth value assignments under which the statement is true. Okay? Everybody get that? So the key here, the goal, is to find the TVAs which make the statement true. In order to do this, we work backwards. We say that the conjunction has to be true, right? Now, the funny thing about a conjunction is, if you remember, in order for a conjunction to be true, both sides must be true. Good. Somebody beat me to it. So both sides must be true. That is, this must be true and this must be true. But what's the main logical operator of the two signs? Well, for the right conjunct, it is this, the conjunction. For the left conjunct, it is the material conditional. Now, because both conjuncts must be true when the conjunction is true, we can attribute, say, a T above this and a T above this. And we're trying to solve for the atomics. Now, this is kind of the nice one because the right conjunct is itself a conjunct. And when any conjunct is true, both conjuncts must be true. So we know already that Q must be true and not R must be true. So we attribute the truth T value to the negation. However, if the negation is true, then R itself must be false. Does everyone remember why? Because the negation must take the opposite truth value. Now, if you look very carefully, we actually have the truth value for Q and R. Q is true and R is false. Okay, that's good. Now, as soon as we have that, what we can then do is distribute the truth values on the other side. That is the left conjunct. Now, suppose I didn't do that. Suppose I didn't say that this is true and this is false. Well, then we would be sort of stuck. Why? Because take a look, the conditional is true. But we know that there are actually three ways in which a conditional can be true. You can have a true antecedent and a true conjunct, or you can have a false antecedent, and the consequent can be false or true. So we don't know what truth values to attribute to, say, the antecedent and the consequent. But because we've started with the other side, because we've started with the other side, we know that Q is true and we know R is false. Okay. Now the conditional, this thing here, must be true, right? But the consequent is false. So we know that the antecedent must not be true. If it were true, if we had a true antecedent to give us a false consequent, then we know the conditional must be false. But the conditional is true, so we know that the antecedent must be false. A false to false is okay for us. So we write false for the conjunct. And we should quickly be able to figure out P, because Q is true, but the conjunct is false, then P itself must be false. If it were true, then the conjunct would be true. So P is actually false. This is the answer on the bottom left. When I ask you to show that this statement is not a contradiction, you would have to solve for the TVAs in this manner, working backwards. Okay? Easy peasy, right? Okay, any questions? Somebody PM'd me and asked me what a TVA is. We covered this last time, but a TVA is the truth value assignment. It is what the atomics are. Good. There's a very good question. How do we know which side to start? So in this case, it's a conjunction. It depends on the actual statement. But if we're talking about strategy, what you want to do is start with the side that's easiest. What do I mean by easy? Well, in this case, there is a unique solution to the right-hand side. When a conjunct is true, there's only one way in which it could be true. And that is if you know your truth tables well, truth tables of the conjunction well, then the conjunct must have, a true conjunction must have two true conjuncts. However, for the material conditional, there are three ways in which it can be true, right? And that's why we sort of left that for later. If there are three ways in which it's true, we would have to do some guesswork, but we try to avoid as much guesswork as possible. Okay, don't worry, we'll pick up more, strategy tips as we go along. I think sort of the best way to learn a lot of these logic techniques is just by practicing. And in fact, I'll let you do so now. Here is a slide. It's a reference sheet. I'm not going to read it through now, but if you ever get stuck, you can refer to this. Okay, now it's your turn. Show me that this is not a contradiction. Okay, I'll give you a minute. If you finished, please write done or finished or something in the chat. As for showing that it's not a contradiction, remember, contradictions are always false, so you have to find one scenario in which is true. And when you're solving, what you're really doing is telling me the TVAs. Okay, I'll give you a minute.